All right, thank you for introduction. I'm Kyoungwoo from Yonsei University in Korea, and this software technique solutions for hardware reliability have been, investigated with collaborators from many of them in ASU, SK Hynix, and ARM. And even though the title is broad, I'm going to talk about one specific software technique today. Reliability is one of the main design concerns in embedded systems because they are deployed for several mission critical applications such as avionics, autonomous vehicles, space applications, and even healthcare applications. So if any error in these systems can cause catastrophic, serious, result. So there are two main, sources to threat hardware reliability. One is software error or transient fault, and the other one is hardware error that is permanent fault. To achieve the reliability, software redundancy is interesting because of the flexibility and its effectiveness. As you can imagine, software level redundancy doesn't have to modify the hardware components, and also it can provide the flexibility and even selective protections. That means you can protect some of components or some modules which are critical. And these software level redundancy have two main approaches. One is instruction level redundancy, which pretty much duplicates instructions and compares the results at a certain point to find out mismatch that is actually error detection. Redundant multithreading duplicates threads in general at physically different hardware components, and they duplicate threads and then compare the result at a certain points so you can find out a mismatch that is an error. Instruction level redundancy can detect soft errors, but not hard errors because, as I mentioned, in general, it can run duplicated instruction at the same hardware. However, redundant multithreading can detect not only soft errors, but also hard errors because they are running at separate hardware components. So today I'm going to pretty much talk about redundant multithreading. This one, software-based redundant multithreading, has been proposed like 10 years ago. And to understand this, we have two duplicate threads. One is the leading thread and trailing thread. And they assume we have a shared memory. So pretty much they have duplicated instructions, identical computation, and at a certain point they compare the results where there were errors or not in this computation. So that certain point is memory operation, and then after they got the memory operation, they check the values for memory operation. So they can compare the results. If there's mismatch, then there's an error. This one has been investigated in these literatures. Pretty much they try to improve runtime, and they try to apply the software redundancy multithreading to other architectures like GPU and high performance computing. But there is some holes that we cannot detect errors. So to observe the error coverage of this redundant multithreading technique, we have developed some fault injection framework, and we studied 9 applications, and we compare original one without protection and SRMT protected applications. And on Gen 5 simulator, we have injected faults, pretty much inject faults at 6 main components, and we inject an error per execution. We inject 500 soft errors and 100 hard errors per component and per benchmark. For fault coverage validation, we consider the number of silent data corruption. Silent data corruption is important because it can result in the incorrect output, even though you have a detection mechanism in your system. So in total, we have several thousand of hard errors and soft errors. And on average, SLMT has some runtime overhead, high overhead. And then we are using 2 cores for physically separated multithreading. But we still can observe several silent data corruptions. This one shows the result. You can see the above one, we can observe about 7,000 silent data corruptions, but still we can see more than 1,000 silent data corruptions in case of SRMT protected. So we have tried to understand what kind of hole they have, and then we have found out 2 error cases. The first one is load operation. So the problem of SRMT is pretty much they compare before the load operation. So since they have identical computation, if they don't have any errors in these computation mechanism, then they check this received address and their locally calculated address. If they are identical, then there is no error, right? But what if there is an error while they are loading the data? Then this load data will be propagated to this duplicate thread. Then these 2 threads have the same incorrect data. So they cannot detect it, then this one is going to generate incorrect output. In case of a store operation, still the problem is they compare the data and address before the store operation. So at leading thread, before the store, they send address and data to trailing thread, and this duplicate thread compares these address and data with their locally calculated ones. If they are no mismatch, that means there is no error. So it is fine. What if when they update the data at the store, there might be some software or hard error? Then it can corrupt the data, then they cannot detect this. So these 2 error cases can generate silent data corruptions in case of software redundant multithreading, which was previous one. Now, how can we recover this? So our idea, actually, that was named expert. Pretty much, rather than comparing the load data, we just replicate the load operation on duplicate thread. So that is, we have shared memory, and main thread and checker thread, they all access the memory and get the data. So we got the load data, and then we got the same load data from the shared memory. Even though there's an error while they are loading the data, still it can just affect one thread. In this example, we just affect main thread. So software on load operation can only corrupt one thread. The good news is we have clean data memory and clean thread. So sometime later, we can detect this mismatch, and then we can detect an error. Actually, checking for load operation is not necessary because it does not propagate incorrect data into data memory. In other words, only store operation can affect the data, the corrupted one, into the memory. So this mismatch can be found on later checking for store operation. What about the store case? We need to think about two cases. One is data corruption. The other one is address corruption. Our main idea is the load back checking against against error. Sorry about that. The main idea is rather than checking before the store operation, we like to check the updated one after the store operation. That is this one. So main thread, we're going to update the data into the memory. If there is an error in the data, then this correct address, we're going to get incorrect data. After the store operation, we're going to reload this data with this locally calculated one. There was no error. And then we're going to compare this load back data with our own locally calculated one. If there is a mismatch, that means something wrong. So we can detect this error. In case of incorrect address, still, if the data, the address is corrupted, then this data is going to be updated at an incorrect, wrong address. And then this one is not updated. So at the checker thread, we're going to load this data after the store operation. Then still, we can detect it. That means we can see the mismatch. So there was an error. So to see the effectiveness of our proposal, we have intensive fault injection campaign, 9 applications, and original one without protection, and the previously proposed one, and our own expert protected. And we consider 6 main components, and then we have lots of fault injections. For fault coverage validation, we also consider the number of silent data corruption. This is the result. X-axis represents the benchmarks that we have studied, and y-axis shows the number of silent data corruption at log scale. And blue one shows the number of silent data corruptions because of soft errors and hard errors, and red one shows the number of silent data corruptions in SRMT, and our own one shows the number of silent data corruption in green color. So if you look at the number, about 20% of faulty injections were revealed as silent data corruption without protection, but still, in case of SRMT, we have observed about 4% of silent data corruptions. In ours, we have just less than 0.1%. That is about 20 out of thousands of tens of thousands faulty injections. So in conclusion, we have improved the detection of hard and soft errors with load back checking and load replication. And then we can achieve about 65 times better silent data corruption coverage. We can see also some limitations. We have high runtime overhead, and as you have seen, this silent data corruption still, we have some silent data corruption cases like silent store. Okay, this is it. Thank you for your listening.
Questions for Kyoungwoo?
Yeah, the system that you're modeling, does it have ECC for the memory system, or is it just a plain non-protected memory system?
Thank you for your question. I'm sorry about not to mention that. We assume, SRMT and ours assume that memory is protected with the ECC. But still, while you are updating the memory, for example, when you calculate the effect address of memory operation, still they can generate some errors. Yes, Aviro? Sure.
So we assume that the memory is protected and there are no errors in the memory. The errors are only injected in the execution, the processor pipeline, right? The pipeline. So the pipeline is not considered protected. The memory is considered fully protected. So in all the components of the processor pipeline, like 6 components that he said, like including register file, load store queue, decode unit,
Load store queue,
the
right.
buffers, reorder buffer, we inject errors in all of them, and that's the result.
Sure.
Do you protect against faults when you're doing instruction fetch and also in the control logic?
I'm sorry, I didn't hear your question.
Do you protect against faults during instruction fetch and also in the control logic, not just the data path?
So you are asking about the protection mechanism for instructions, right?
Yeah, and in the control logic of the processor.
Yes, that's a good question. But in case of this particular work, we didn't consider, control flow checking pretty much. But this software redundant techniques, multi-threading technique, pretty much we consider, interesting synchronization points. That is memory operation, like load operation and store operation. Pretty much we focus on load operation and store operation. But because if something's up, like any error, then it's going to generate some errors, and it's going to affect, to registers, for example. And if you update this incorrect one, erroneous one to memory, then we cannot do anything, right? So at the memory operation, we like to check there was an error or not.
Maybe a slightly different way of asking it, the same question is, what would be the effect of considering the actual hardware implementation of the design versus doing the faulting in Gem 5?
Oh. Whew, that's a good question. If we have a real hardware, and then if we have real framework to generate, inject the faults in real hardware, that would be great. We don't have that kind of system, so that's why we are using Gen 5 simulator. If this Gen 5 models the hardware, all the architectures at RTL level very correctly, then I think the output or the comparison would be valuable. But there might be some difference, like absolute number of silent error corruptions.
Yeah, that's often the case where there's not a one-to-one correspondence between things in the model that you're looking at and wires or registers in the actual implementation.
Right. So the real absolute number of silent error corruptions or errors would be different, but I believe still the relative effectiveness can be the relative effectiveness can be still valid.
Yeah, I think so too.